Hi everyone, I'm Saksham and I'll present about our research on sound source distance estimation in diverse and dynamic acoustic conditions. Currently, I'm a PhD CS student at University of Texas at Dallas, and this work was done during my master's at NYU. I'm really thankful to my co-authors and mentors, Iran, Magdalena, and Juan from NYU. Sound source localization is the task of finding the location of a sound source relative to a microphone. It can be broken down into two subparts: the direction of arrival of a sound in terms of azimuth and elevation angles, and the distance between the sound source and the microphone. It has many applications such as sound source separation, audio-based navigation, and urban surveillance. Recent research has focused on direction of arrival estimation, while distance estimation remains understudied, majorly due to it being a difficult task because of factors like reverberation, reflections, and background noise, and also due to the absence of annotated data, which limits the usage and effectiveness of data-driven approaches. Previous attempts are not generalizable, as they have tried to tackle this problem by reformulating it as a classification problem over specified ranges, or testing their approaches on small synthetic data or a handful of real data. Here is how we try to tackle this problem. We have added distance annotation for a collection of open source datasets that were previously only used for DOA estimation. We use a CRNN-based model that is able to estimate the distance of non-simultaneous static and moving sound sources. We show the effectiveness of our approach through comprehensive testing on diverse dynamic uh, environments and acoustic conditions. We also provide the analysis of model performance resulting from using different loss functions. And we found that percentage-based regression losses provide optimal performance. In the past, researchers have focused solely on determining the direction of sound rather than the distance. Most recent deep learning approaches in DOA have used convolutional recurrent neural networks or CRNN and have benefited from open source datasets and room impulse responses based data generators. We've we found that we all could adopt these DOA models and datasets for distance estimation. If an oracle could tell us about the onset time of sound, we could easily calculate the distance using the speed times time formula, but this is not possible. And previous attempts at distance estimation have been inspired from human listening, like using the direct to reverberant ratio and data-driven approaches with simplified objective and non-coincident mics. For our natural distance estimation setting, we could only find one baseline that uses generalized time domain velocity vector-based representation to estimate distance, which basically uses temporal relations between sound sources wall reflections to infer the delay of propagating signal. We have used 5 datasets consisting of eigenmic recordings with moving sources and diverse acoustic settings. Precisely, we use decays, that is a generated dataset, and it is generated using room impulse responses and is largest in our study. Next is stars, which is the largest real data that we use in our study and has been modified to mask the overlapping paths with corresponding room background noises. This is because our model currently can only be used for non-simultaneous sound occurrences. Next, we use Locata, which consists of a single room speech recordings and is used in the study by Daniel and others that we use as one of our baselines. Marco consists of music recordings in a church, while metadata consists of 3D grid room impulse responses in an office setup. Here we have shown some statistics about all the data sets that we have used. And the differences in these data sets is what makes our problem challenging and worth exploring. We modified the CRNN from Advani and others to detect the presence of event and predict distance. Distance output should make no sense and should be ignored if the sound is not present. Hence, we optimize a multitask loss which consists of event presence detector and masked distance estimator. We do a two-step training. First, we train the sound detector over decades data, and we call this pre-trained sound event detector or PSED. Then we do multitask training of sound detection and distance estimation. We do several testing to estimate the benefit of retraining over bigger data and fine-tuning and adapting over smaller data sets. Note that all of our models are initialized with pre-trained sound detector. We also experiment with several regression loss functions for distance estimation. Apart from apart from the standard L1 and L2 loss, we introduced percentage-based losses that basically divides the loss by true distance. The key idea behind this is that a zero point 0.1 meter error for a true distance of 1 meter should have higher loss when compared to a zero point 0.1 meter error for a sound source that has true distance of 10 meters. And here we have shown the exact formulation of the losses. We test our model using three experiments, uh, that is comparing with a baseline, mm, mm, and then the effectiveness of a model when pre-trained over a larger data set, and how does different losses uh, affect the training. For our first experiment, we compare our CRNN-based approach with a recent proposed signal processing baseline and an average distance computed on the training data. We we follow the metrics that were proposed in the baseline paper, that is mean, median, and standard deviation. Again, to revise, trained with Logata is initialized with a sound detector and trained further with Logata dataset. And FWLS is is actually uh, a model that is initialized with a sound detector and then pre-trained with stars and fine-tuned with Logata. Here, the best epsilon refers to the best loss function that we found. And from our experiments, we observed that our models improve as compared to the baseline on all metrics, and pre-training with bigger data sets help improving the performance. Percentage error based loss functions perform better than the standard losses. Next, we compare the predicted and ground truth distance values for two test sets examples, and we see that the predicted distance indeed follows the ground truth distance over time. Next, we try to see if the benefit of pre-training over bigger stars dataset is generalizable or not. Hence, we compare pre-training over stars followed by fine-tuning with simple training over the target data sets, which are DKs, Metu, and Marco. And again, we observe the same results that pre-training with stars help and percentage-based error losses show improvement. We further try to explore the effect of different losses and the reason for the benefit of percentage-based errors. We compare the performance of different losses over Locata test data. We see that thresholded percentage error based loss performs best, and percentage error losses in general perform better than standard L1, L2 losses. As shown in the figure, we can refer that this is due to the standard losses like L1 try to reduce errors for far true distance more. Meanwhile, percentage error losses uniformly try to reduce the error with respect to ground truth distances. Uh, as we can see, the blue, which is the absolute distance, it it has lesser loss for bigger ground truth, while for the smaller ground truth, it has larger uh, error as compared to other percentage-based errors, which have comparatively more uniform error with respect to ground truth. In conclusion, we extended the DOA datasets and models for distance estimation. We proposed a generalizable training schema that is effective over diverse acoustic environments. We improved distance estimation using percentage error-based loss and pre-training. And in the future, we would like to extend our approach to work on multiple simultaneously occurring sound sources. And we also want to have a joint model for direction of arrival, estimation, classification, and distance estimation. Thank you.